So today we're going to do lesson 4.2b, mainly about completing the square, but we'll also talk about vertex form and standard form of a quadratic. So when we talk about standard form, this is standard form, something like this: y equals ax squared plus b times x plus c. You can see that this is clearly the standard form, and we'd like to convert this to vertex form. Vertex form is y equals a times x minus h 20 squared plus k. And we've worked with both of those forms a little bit in the last couple weeks. And so we're going to now try to convert this to that form, because there are some real advantages to converting the forms here. When we look at the graph, there's some advantages to each form. If you want to just kind of roughly kind of get an idea about it, the only thing we know from the graph right now, just from the standard form, basically right now, so far, we know that it has a y-intercept of 5. If you plug in 0 for x, it's going to hit at the point 0 is your x value and 5 is your y value there. So the y-intercept is clear on vertex form, or on standard form. That's c is always the y-intercept of the graph, which is helpful to know the y-intercept. So let's do the steps and convert this and see if it helps us really graph this problem or not. So the first step in complete the square is move the constant. When I say move the constant, maybe I should say add or subtract the constant to get it to the other side. In this case, the constant is c, so this 5, I need to move it to the other side. We're going to do that by subtracting 5, inverse operation, from both sides. So on the left-hand side, we get y minus 5 equals x squared plus 2x. I'm going to put plus blank. I know I'm going to add something there in just a minute here. It's kind of 0 right now, but I'm going to make that a perfect square. The goal of completing a square is to make this a perfect square trinomial. So the second step, should it be necessary, is make sure the lead coefficient must be positive 1, be equal to 1. In this case, the lead coefficient is 1 right there, so we're okay. If not, you would divide each and every term by the lead coefficient, So that would be your second step. That's not necessary in this case, so you don't always do the second step. We can just skip that in this case. Third step we've done before with complete the square. Hopefully you remember it. You take half of this number, so half of, in this case, b. So half of b, then square that value and add to both sides. Okay, so I'm going to take half of this number 2. Half of 2 is 1. 1 squared is 1. So I'm going to add 1 to the right-hand side. I'm going to add 1 to the left-hand side. So on the left, I get y, minus 4 equals. On the right, I know that's a perfect square right there. It's got to be. I added half that middle number squared. It's set up like a perfect square. The square root of 1 is 1. There's a plus and plus, so I know that's plus. That's the factored form of x squared plus 2x plus 1, which is a perfect square trinomial. So if you square the binomial x plus 1, you'll get that. Last step, so kind of like the first step, you move the constant back over. So move constant back over to the other side. So when I move that 4 over, I'm going to add 4 to both sides. And I get y equals x plus 1 quantity squared plus 4. From there, that's a +1. That's hard to read there. From there, you can identify using the formula for vertex form. So vertex form is very good at identifying what h and k is. So h would be, in this case, h and k would be -1 would be h, and k would be +4. So my vertex is at -1, 4. And let's see if we know anything else from this. So the axis of symmetry, well, it's going to be right there. So maybe I should draw that. It's going to be a dotted line. Got to go through the vertex. That red point is the vertex. So at x equals -1, which is the same thing. If you're looking for a formula, that would be x equals h is the axis of symmetry. And so there's a line at x equals -1. I would always label that equation. So you actually do know another point, because parabolas are symmetric, so there must be a point right there. In fact, we could do a really rough sketch of this parabola. It might do something like this. I'm not sure where the next point is, but we know 3 of the points, and I'm running out of graph space, so I might be able to do that. I'm not sure if graphing is part of the lesson here, so I'm showing that extra here just so you see it. The key is we want to get it into this form, complete the square, so it's in that form, and then we should be able to identify the vertex of the parabola. Now we're going to use standard form to graph. Is that the same parabola? No, it's a little different. Okay, just checking. Okay, so we're going to use standard form to graph this parabola. So for this, again, the thing we know from this form, oh, it has the same y-intercept, doesn't it? Y-intercept is 5. So we know there's a y-intercept at 5. That's what we know from standard form. And the other thing we know, if you look at the quadratic formula, so you remember the quadratic formula, I always like to split it up. I like to write the opposite of b over 2a plus or minus, and I know a lot of people write it together, but I write it more like this. Square root of b squared minus 4ac. The key thing I want you to focus in on is this is essentially the axis, or the middle of the graph, the axis of symmetry. Let's look back at this problem. So look at this one. Let me just kind of bring this down. Oops. So give us some room here. So I'm going to pretend to start doing the quadratic formula on this. So I'm going to say x equals the opposite of, let's see, b, which would be opposite of 2 over 2 times 1, plus or minus, that's over 2 square root of what, 4 minus 4 times 1 times 5. So it ends up being something like -2 over 2, which is -1, plus or minus 4 minus 20, which is square root of -16 over 2. I guess this simplifies a little bit. This is maybe not the best example to use to drive home my point here. But I do want you to see something. The axis of symmetry is -1. But the axis of symmetry is x equals -1. The way we got that, it's part of the quadratic formula. It's this first part. This is h, if that makes sense. That's always going to be the middle of the graph. So we have a formula. This is equal to, remember the formula for the axis of symmetry is x equals h. We could also say this is equal to the opposite of b over 2a. So if the parabola is in this form, standard form, I'm just going to apply this part of the quadratic formula first to figure out where my axis of symmetry is. So to do that, let's try this way. So we're going to go x equals the opposite of b, which would be the opposite of 6, over 2 times a, which is 1. So this is -6 over 2, which is -3. So I know there's an axis of symmetry dotted vertical line at x equals -3. That's the h value of the vertex. The vertex is somewhere on that line. I'm not sure where it is, but it's somewhere on that line. So to find it, actually what's interesting is if we plug -3 into the function, everywhere there's an x, we're going to plug in -3 here. Let's see what happens. We get y equals, instead of x squared plus 6 times x plus 5, I'm going to plug in a -3. Both cases. -3 squared is 9. 9 minus 18 plus 5, let's see, that would be 14 minus 18 is -4. So the y value of this point is -4. So there it is. By the way, since I know parabolas are symmetric, if there's a point at 0, 5, there must be, if I count this over 3 units left, there must be a point there. I know that's a lot of points, but if I have the intercepts, vertex, I could graph a really rough sketch of this if I wanted to. Something like that. Roughly. Really bad effort there. But if you use standard form, you could get it just from figuring out what the axis of symmetry is, maybe the y-intercepts. Might be nice to also find the x-intercepts there. The method there is to find h by plugging in the formula h equals the opposite b over 2a, then plugging that answer back into the original equation to figure out your y value. So now let's try to make this into a vertex form. So this is, again, going back to the complete square method. So I'm going to subtract 5 from both sides. Get y minus 5 equals x squared plus 6x plus blank. When I know what you get there, so half that number squared is 9, so I'm going to add 9 to both sides. I get y plus 4 equals, this should be a perfect square, x plus square root of 9 is 3. Last step, I'm going to move this 4 back over, in this case by subtracting 4 from both sides. So we get y equals x plus 3 quantity squared minus 4. So we get the center is going to be at -3, comma, -4. So -3, -4 is the vertex, or sorry, that's the vertex. H, okay. The y-intercept is +9. That's way up here. Somewhere up here is, at 0, 9 is the y-intercept. And then so the axis of symmetry. Of course, this would be the middle of the graph. Would be x equals -3. If this is 0, 9, if I go 6 units to the left, that would be the point -6, 9. And I could probably sketch my parabola something like this. This is a really nice graph, hard graph for this. You got it. So you can try a few more using either equation or method to do that. And working backwards, I think vertex form might be the easiest way to tackle a problem like this. Helps know what transformations have happened. So in this case, we see the vertex is at 4, 5, which are h and k. So we know this is y equals, I don't know a yet, I'm running the blanks for that, x minus 4 quantity squared plus 5. So I do see a pattern here. Let's see. So wow, it goes down to. So I don't know what a is. I do know that h and k are there. But I also know these other 2 points. I'm just going to label this one. This would be the point 5, 3. And that's really an x and y point. There's lots of x, y points. So to solve this equation, plug these 2 values in for x and y and solve for your missing variable, which is a. That's the end of the screen cap.